Work and kinetic energy. Let's say we have a constant net force acting on this object of mass m, and the object is displaced by an amount s due to the force. The force vector is in the same direction as the displacement vector to the right, which we will call the positive direction. What does Newton's second law say? It says that this net force is accelerating this mass, which means that the velocity of the mass changes from a value of v initial to a value of v final. Since the motion in this case is linear, we can equate just the magnitudes of these vectors. Multiplying both sides of this expression by the magnitude of the displacement, we get s times sigma f equals s times m times a. This term, displacement times force, should look familiar. It is the work done on the object by our net force in this case. What if we want to see how the work done relates to the initial and final velocities? One of our kinematic equations says that the square of the final velocity is equal to the square of the initial velocity plus 2 times the acceleration times the displacement. If we solve this expression for a times s, we get 1/2 times the quantity v final squared minus v initial squared. We can now substitute this expression in for a times s in this equation. Doing so, we get this equation, which we can rewrite in this way. This equation is our objective. It's called the work-energy theorem. The work-energy theorem relates the work done on an object to how the kinetic energy of the object changes. Kinetic energy can be thought of as energy of motion, and the kinetic energy of an object with mass m and speed v is given by 1/2 times m times v squared. Kinetic energy is in units of joules, just like work, and kinetic energy is a scalar quantity because it does not have a specific direction. So in this equation, we see that the term on the left-hand side is the work done on the object by the net force. This term, involving the final velocity of the object, is the final kinetic energy of the object, and this term is the initial kinetic energy of the object. So, when a net external force does work on an object, the kinetic energy of the object changes from its initial value to a final value, the difference between the two values being equal to the work. Let's do an example problem. How much kinetic energy does a 30 kilogram box have if it is moving with a speed of 3 meters per second? And part B, how much work is needed to increase the speed of the box to 5 meters per second? What are we given in part A? Our box has a mass of 30 kilograms and it's moving with an initial speed of 3 meters per second. And what is part A looking for? The kinetic energy of the box. So, for part A, what equation can we use? Kinetic energy is equal to 1/2 times mass times speed squared. So we can use our initial speed to find the value for the initial kinetic energy of the box. So we plug in our values for m and v initial, and using our calculator to solve, we get a value of 135 joules for the initial kinetic energy of the box. Now, for part B, we're looking for work. How much work it takes to increase the speed of the box to a final value of 5 meters per second. So we are given a v final of 5 meters per second. What equation will help us with part B? We know that the work done on the box is equal to the box's final kinetic energy minus its initial kinetic energy. Now we just need to get this equation in terms of things that we know. We've found the initial kinetic energy in part A, and we know that the final kinetic energy is equal to 1/2 times the mass of the box times the final speed squared. So we can substitute this expression into our work equation. And now we can plug in our known values for m, v final, and the initial kinetic energy. And using our calculator to solve, we get a value of 240 joules for the work needed to increase the speed of the box to the final speed.